Hi everyone, we are the Spartan Superway Boogie Chassis Team. Our team consists of 9 members, and the person to introduce the project will be Andrew.
Spartan Superway is a project designed to implement a personal rapid transport system using renewable energy. The Spartan Superway plans to revamp the public transportation system by introducing renewable energy, autonomous vehicles, and transportation efficiency in our modern world. The picture on the left resembles a hypothetical scenario of what the Spartan Superway would resemble. What overall problem does the Spartan Superway project address? The project will address CO2 emissions, using renewable energy sources, and slower and costly transportation. It will address CO2 emissions by using solar panels. According to the Center of Biological Diversity in California, transportation is the leading source of greenhouse gas pollution, accounting for about 40% of the state's emissions. Fossil-fueled transportation emissions also create smog, soot, and other harmful air pollution. The picture on the right shows greenhouse gas emissions associated with human activity in the United States. As you can see, the transportation sector alone accumulates 28% of total greenhouse gas emissions, taking the largest portion of the chart. The Spartan Superway will use electrically powered bogies from renewable energy from solar panels, thus reducing the large amount of emissions. Also, there will be no traffic and no stops, and the vehicles will all move autonomously. What problems will our chassis team be addressing this year specifically? The battery is going to be powered on renewable energy from using a solar panel at the design center. This will help the overall goal of the Superway to use renewable energy, which ultimately helps reduce the CO2 emissions. The chassis we're building is a prototype that can sit around 6 people. This will help the goal of the Superway to have independent and fast pods with no stop. And in our modern world, independent pods would be very useful, as we have seen from COVID, for safety reasons. Next, we will have Christian to talk about the state-of-the-art review.
Thank you, Andrew. While doing our research, we understood that there are teams that have worked on the Spartan Superway project in the past. So we are doing our due diligence by learning what we can from their projects, and this means improving on past designs and building off the work that has been done before us. We are also analyzing existing infrastructure to give us an idea on where and how this type of transportation has been implemented. We are pulling design inspiration from existing products like Transit X and the railway in Wuppertal, Germany. Transit X builds and operates a privately financed public transit podway that can transform cities and metropolitan areas to be green and walkable. Their work is very similar to that of ours, and they also prove that there's an interest and a market for PRTs. Lastly, the Boogie and Chassis team are also drawing inspiration from similar designs like the railway in Wuppertal, Germany, which exemplifies an existing design that is similar to what we seek to achieve. For the next slide, Jake will talk about electric specifications.
The main goals for the electrical team are to provide power for the bogie actuators and to the switch arm, to collect and handle data from the sensors, to send and receive data to the riot team and the track team, to provide control software for the bogie, allowing us to stop at desired locations, and to interface with the wayside power system. Because of the variety of operations we are performing, we decided that an ESP32 would best fit our needs. The ESP32 will be able to communicate through Wi-Fi with other teams. It will gather data from the sensors using either I2C or SPI communication. It also supports both CircuitPython and Arduino code, so we have a lot of flexibility in that area. I'm going to pass it off to Devin to explain how all of these systems will interface.
The electrical design will be composed of a hub motor, electronic speed controller, battery, power board, microcontroller, position sensor, object detector, gyrometer, and accelerometer. The Feather ESP32 will be the central hub that controls the hub motors, collects data from sensors, and communicates to IoT and track team through onboard Wi-Fi. All components will be powered by a single battery pack. The gyrometer will sense tilt in the bogie, particularly while turning, and the accelerometer will measure bogie acceleration and deceleration. Position sensor will detect where the bogie is on the track, while the object detection sensor will detect other bogies or objects that may block the track. All sensor data will be transmitted to IoT and track team, while the feather also receives data from both teams. Now I'll hand it off to Max to talk about the mechanical design specifications.
There are several specifications for the mechanical design portion of the bogie. First, there must be sufficient space and effective fasteners for the attachment of the switch arm mechanism, as well as all the electrical components. The bogie design must also navigate the existing 10-meter track without any assistance. The small-scale bogie must also allow for the attachment of a carriage on the underside and support a load of 100 pounds applied at that connection point. There also must be a suspension system. This is implemented so that the carriage does not experience heavy vibrations from the track. And lastly, to ensure the safety of our passengers, the bogie will be designed using a minimum safety factor of 2. And next, Carlos will go into the progression of our design.
The bogie is one of the main mechanical components to consider and designed to be integrable with all the other components within the system, such as switch arm, track, and electrical components. As a team, we have taken inspiration from bogie designs incorporated into trains that have shown to be an optimum design. Our bogie will take various components from train, such as suspension and frame. Various other components are unnecessary and opted out of our system. Next, Alex will explain the design challenges.
Right, so we anticipate multiple design challenges based on this for this whole project. One of the biggest ones we anticipate is collaboration. Working with such a big team and being the Boogie Chassis Team specifically means we have to work a lot with the IoT, switch arm, and rail team in order to ensure that the design is as well integrated as possible. This means that we have to do constant communication between all the teams to ensure that no team is hard stuck and waiting for certain group design decisions. Additionally, because of the addition of IoT, we anticipate a major challenge with how we're going to quickly transfer data to and from IoT, because certain processes on the tool require accurate, quick sensor acquisition in order to achieve certain goals. Additionally, when we looked at previous design teams' work, they mentioned difficulties that they had. For example, 2016's design team had asynchronous components due to manufacturing defects, and this led to switch arm failure during their design. So we have to ensure that our manufacturing process is accurate and as simple as possible. Additionally, 2019's design team had difficulties with integrating electrical components and using Wi-Fi on board. So we have to ensure that we are early on the ball when it comes to integrating electrical design and validating our Wi-Fi and general communication standards on the bogie itself. Now I'll be passing it off to Hussein to discuss how we're going to plan this whole process.
So this is a detailed chart of the task for our project with deadlines specifying the time required to complete them. Since we have a big team with two major subteams, systems and multiple subsystems, we plan to do our tasks simultaneously for each of those subsystems. To execute this, we're going to be in constant communication with each other to meet the goals of this project and make sure the deliverables and contingencies between us are crystal clear. However, we have a conservative time estimate for each of those tasks because we wanted to factor in the miscellaneous roadblocks that would occur along the way. I'm also going to be followed by Michael now, who will talk about the team members and how they're distributed for the subsystem.
For this project, the Boogie Chassis team will be split into two branches, mechanical and electrical. In this diagram, you can see that Carlos, Max, Christian, Andrew, and I are part of the mechanical team. Jake, Devin, Hussein, and Alex are part of the electrical team. For the mechanical team, there are two phases. Phase 1, all the members will be responsible for designing and performing analysis on the Boogie chassis. Then, the mechanical team will collectively transition to suspension. And again, in phase 2, all the members will be responsible for the development of the suspension system. For the electrical team, they will be focusing on selecting and programming the sensors for the bogie. Within electrical, there is a power sub-team, and they will be focusing on how to power the sensors in the bogie. This concludes our presentation. Any questions?